Hello, ladies and gentlemen. Let's take a look at question 9. When a liquid is boiling, thermal energy must be supplied to maintain a constant temperature. How come? Now, when a liquid is boiling, two things happen, right? So inside a liquid, basically there are molecules, and they are quite uh, bonded together. In terms of water, I think you can say that there are hydrogen bonds, okay, bonding water molecules together. Now, in order to make it boil, so this is what happens during boiling. There will be a big bubble formed. Now, this bubble, contrary to what many people might think, is not made of air. It's made of water. In fact, steam or water vapor. Okay. So inside this bubble, the air molecules the water molecules are moving, all right, freely inside without any bonds. Okay, so this is H2O moving without any bonds. So basically what has happened is that number one, the bonds between the water molecules have actually been broken. And this takes energy, all right? So the bonds have been broken. Now this kind of bond is the intermolecular potential energy of the molecules. Not only that, but something interesting has happened. Do you know that when the bubble expands, what happens is that the water level rises. So there's an increase in the water surface height. Now, that's because the bubble itself, expands and then it pushes the entire surface up. That means to say the surface has pushed against the atmosphere. Now remember that the atmosphere is trying to squish the water back down, but whenever you have a big bubble, it's actually pushing against the atmospheric pressure and it causes the water level to rise. Now, this is kind of like having a piston expand against the atmosphere. So, this expansion requires a lot of effort. The amount of work done by the expansion will be P delta V, where V is the volume of the bubble that's expanded. So there will be a new work done in order to expand the bubble, okay? And so there is also work done against the atmospheric pressure. Now, this is the work done by the bubble, okay? The bubble vapor, okay? Now, so there's two kinds of energies that's required. All right, one of them is the energy to break the bond, the potential energy, and then the other one is the work done against the atmosphere during expansion. So these are the two energies. Now, what happens when you boil water in vacuum? Now, in when you boil water in a vacuum, then there is no atmospheric pressure, so there is no work done. uh, well, or rather negative work is done because you're pushing against zero pressure. So what does this mean? This means that in space or high up in the altitude where the atmospheric pressure is lower, let's say on Mount Everest, you require less energy to boil water because you don't need the water to do work or do less work against the atmosphere. Okay, so this is the explanation for how water boils and why water boils at lower temperature if the air pressure is lower. Now, so next we have a heating experiment. Energy is supplied at constant rate to this heater. And then when the liquid is boiling at a constant rate, the mass evaporated in 5 minutes is measured, and then you do it twice. Now, why do you do this experiment twice? That's because there is thermal energy loss to the surroundings. Now, what happens is that the thermal energy loss to surroundings occurs at the same rate in both experiments. How come? Why does thermal energy loss to surrounding occur at the same rate in both trials? That's because the rate of the thermal energy transfer is dependent not only is dependent on the temperature difference between the object and the surroundings. Now, so why should this be the same? Because the liquid will boil at the same temperature. in all trials. So the thermal energy loss, the rate of thermal energy loss is the same for all trials. So by repeating the experiment and subtracting the results, we can eliminate the heat loss. Okay. Now, let's take a look at what kind of uh, formula we're going to use for this. Now, we know that in boiling, we use this formula where the heat added goes to break the latent heat of break the bonds, and meaning that the heat is used for the latent heat of vaporization. However, uh, when there is a heat loss, okay, then there will also be a heat loss term. All right. Now, in A levels, we don't just use heat transferred, we use the power transferred over a unit time. So this ml plus the heat loss term. Okay. Now then the power is equals to m over t L plus h loss over t. Now it is precisely this rate of heat loss is the same for different trials. So what does this mean? Now this means that if you have two trials, then you put P1 equals to M1 L over T plus H. Then the next one is P2 equals to M2 L over T plus H. Then if you take 2 minus 1, equation 2 minus equation 1, you get P2 minus P1 is equals to M2 over T minus M1 over T bracket L. The heat loss term will cancel out. Okay, so let's see how this works over here. Calculate in joules per gram the specific latent heat of vaporization of the liquid. Now we do two trials, one at 50 watts in which 6.5 grams is evaporated in 5 minutes, and then another one at 70 watts where 13.6 grams is evaporated in 5 minutes. So we shall use the formula power is equals to ml over t plus h. Okay, so we can fill in the first values over here, and then the second values over here, and then you subtract 2 from 1 to give L is 845 joules per gram. Okay, and that's the end of question 9. All right, let's take a look at question 10. The first law of thermodynamics, delta U equals to Q plus W. Now, in this situation, an ideal gas undergoes a change, and for each of the changes below, indicate whether delta U, Q, or W is 0. Now, let's take a look at the first law of thermodynamics. The first law of thermodynamics states that the increase in the internal energy of a system is the sum of the heat supplied to the system and the work done on the system. Now, I want you to take a look at the highlighted words. They are very important. Okay, because some students will write, the change in internal energy of the system is the heat supplied and the work done, which is completely wrong. You must tell me whether it's increase and heat supplied to the system or from the system or work done on the system or by the system. These words are very important, so don't get them wrong. Now, for delta U, for ideal gases, the change in internal energy of the system is proportional to the temperature change. Okay, so what do I mean by that? Now remember that uh, for ideal gases, the total kinetic energy, the kinetic energy of average kinetic energy of a molecule is given by 3 over 2 kT. And then so the total kinetic energy of a system is given by 3 over 2 nkt. And so this means that it's related to the temperature of the system. Okay, so this means that the internal energy of ideal gas is 3 over 2 kT, and the change in internal energy of an ideal gas is 3 over 2 nkt and delta T. So This means that the change in internal energy of an ideal gas is proportional to the change in the temperature. So let's take a look at some of the situations that we are given. Okay, a change at a constant temperature means that the internal energy is not changing. Okay, now if the container is insulated, then there can be no heat supplied to or from the system, and Q will be zero. If the change occurs inside a rigid container, the container cannot expand or contract, and so the work done on the gas or by the gas will be zero. And if there is a sudden change, then there is no time for heat to be transferred, and so the heat transfer will be zero. Now, let's talk about the names, okay, for each of these changes. A change at a constant temperature is called isothermal change. A change inside an insulated container where the heat transfer is zero is called an adiabatic change. A sudden change when the heat transfer is zero is also called a adiabatic change. And the change inside a rigid container is called an isochoric or isovolumetric change. Okay, there's no need for you to learn all these words because they won't be tested in the A levels, but they will be taught in university. So why don't you just learn the proper names right now? So that's the end of question 10. Now let's take a look at question 11, which is also on the first law of thermodynamics. An ideal gas undergoes a change. For each case below, indicate plus, minus, or zero for the changes in internal energy, the work done on the gas, and the heat transferred to the gas. So the first thing that I like to do is to write the words on, work done on the gas and heat transferred to the gas, so that I know which direction the heat and the work is being done. Now the gas is heated by an external heating agent. So this is heat transferred to the gas in a rigid sealed container. Rigid and sealed means that there is no change in the volume. So if there's no change in volume, then the work done will be zero. So think about it. You add heat to the gas and don't allow it to expand, the temperature must go up. So this is intuition. So there is no way there is you must have been able to think about it in your mind. All right, what will happen if you heat the gas and don't allow it to expand? Alternatively, you can also use this equation, which I believe that you should use your mind to imagine the situation first rather than going straight to the equation. Okay, Ken? So that you can build up your physics instincts. Next, the gas expands gradually. Now, whenever there is an expansion, that means it's work done by the gas. So if work done by the gas, then work done on the gas will be negative because it takes energy, the gas uses up its internal energy to expand. Next, it is happening at a constant temperature. Constant temperature. So if you expand the gas, it should cool down. So how come the gas is not cooling down? This means that as you expand the gas and it's trying to cool down, you must supply heat to the gas in order for it to stay at a constant temperature. So let's fill in some values here. So the work done on the gas is negative due to the expansion of the gas. The change in internal energy is zero because it's at constant temperature, and therefore there must be a heat supplied to the gas. Now, if you don't like to think about this instinctively, then why don't you think about it, okay, through a diagram, and then you can look at the piston moving. So the piston moves out at constant temperature. So the work done on the gas, let's say, is minus 10 joules. The change in internal energy is 0 joules. Therefore, using delta U equals to Q2 plus W on, then 0 equals to minus 10. Q2 must be plus 10. All right, so this is how you would solve it mathematically by giving in some fictitious values so that you can work out the numbers. All right. Now, next, the gas cools at a constant pressure. For part C, it is a good idea in order for you to draw the PV diagram. Right? So here's a PV diagram. I'm going to draw two isotherms. This is temperature hot and this is temperature cold. Right. So a process that occurs at constant temperature pressure, a gas cooling, that means to say the pressure is constant. It must move along this line and it must go from a hot temperature to a cold temperature. You can see that the process is going from A to B along this isobaric pressure line and it's going from a high temperature to a low temperature. This means that actually work is being done because there's a volume change. The initial volume is over here and the final volume is over here. So the gas has contracted. So there is a contraction of the piston. Now, whenever there is a contraction of the piston, work is done on the gas. Okay, so the work is done on the gas. Now, and then it's cooling. If it's cooling, so this is a negative. The temperature has dropped. That means the change in internal energy will be negative. All right. Now, if you think about it, over here, this piston is at constant pressure, so everything inside the piston is always at atmospheric pressure. And then the gas cools down on its own and contracts. Now, how is it possible to cool down on its own and contract? That means the gas must have transferred heat outside to the environment. It has been cooled down by the environment. So this is a cooling of the system. Okay. So you can also put in numbers if you're unsure, okay, to actually work out the values. And that's the end of question 11. Now let's take a look at question 12. A fixed mass of ideal gas in a heat pump undergoes a cycle of changes as follows from A to B, B to C, then down to D again. Now, a heat pump usually means refrigerator. Okay, so usually means refrigerator. Now, why is it called a heat pump? Because it pumps heat from the inside of a refrigerator to the outside of a refrigerator. Okay, sometimes the heat pump works in the opposite direction to take the heat from the environment and put it into a room, but that's very rare. The table below shows some energy changes in a cycle A, B, C, D. Now the answers are shown, okay, in this diagram over here. I think this should be the answers, if I'm not wrong. Okay. Now, so let's now start with putting in all the zeros that we know first. Okay. Now, let's take a look at some of the simple zeros over here. The simple zeros that I look for will be any vertical line. These are called isovolumetric processes. And in an isovolumetric process, the work done is zero because uh, isovolumetric or isochoric. And the work done is zero because the work done is P delta V. So since delta V equals to zero, so W equals to zero. So the first two that I'll write will be from B to C is zero, and from D to A is also zero. Okay, next, I'll look for any horizontal line that has two data points uh, shown. So let's take a look at the first line and the second line. Over here, the first line and the second line. Okay, just to double check, there is heat supplied to the gas and work done on the gas. That's great. That means that this equation can be used. Delta U equals to work done on the gas plus the heat supplied to the gas. Okay, so the increase in internal energy, this is doing for A to B, is equals to the heat supplied to the gas plus the work done on the gas, which means that the work done will be 1,200 joules. Now we're going to do the same for C to D as well. Okay, the internal energy, increase in internal energy of the gas will be equal to the work done on the gas plus the heat supplied to the gas. So we're going to fill in this number as well. Okay, now what's the next number that we're going to fill in? Well, the next number that we can fill in will be B to C. Okay, why B to C? Because over here in B to C, the increase in internal energy of the gas will be the sum of the heat supplied to the gas plus the work done on the gas. Okay, so that means Q2 will be equals to minus 1350. Okay, now the last line that we can do over here will be the line D to A. Now in D to A, we will use the principle that in a closed loop process, the sum of all the delta U will be zero. Let me just get this correct. Okay, so we add all the changes in internal energy, it must equal to zero. Now, why is this the case? Because the processes end and start, the closed loop start and end at the same point, which means that the start and end have the same temperature. Okay, so remember every point on the diagram is a PV equals nRT equation. So if it starts and ends at the same point, it must have the same temperature. So let's do this. This plus this plus this plus this equals to zero. So if you work out the math, this will be 750. Okay, and if this is 750, then this is also 750. So there is an order in which you do this uh, puzzle. Okay, and the order you to do this puzzle is first you look for any zeros. So you look in the diagram, there are two processes with zero work done. So you put in 1 and 2 is bubble 1 and 2 will be 0. Then you look for horizontal parts of the table. If there's two data points filled in, then you can fill in the third data point as well. So that's the first, second, and third lines filled in. And then the fourth line, usually you have to make use of the fact that in a closed loop, the sum of all the changes in temperatures must be equal to zero. Okay, so that's the end of question 12. Now let's take a look at question 13. The variation in volume of the pressure of an ideal gas as it undergoes a cycle of changes is as shown. Now, let's take a look at the interesting cycle, just a bit of trivia. Because it's a clockwise cycle, so there is this thing called the net work done by the gas is positive. Now, if the net work done by the gas is positive, this is a heat engine, otherwise known as just a steam engine or internal combustion engine. Basically, this is a engine that takes in fuel and outputs work. Basically, any engine in a car or train does this. The temperature of the gas is 290 K, so let's fill it right in the numbers here. The temperature at B is 870 Kelvin. During the process B to C, 800 joules of work is done. Okay, this is work done is minus 800 joules. Because we know that it's done by the gas, so it is negative. The table shows delta U, the increase in internal energy, heat supplied to the gas, and work done on the gas. So very good. All the terms are the correct terms, so we don't have to switch any of the signs. Now let's take a look at the data in the table. We only have two pieces of data and almost everything else is unknown. So what can we fill in first? Well, let's look for vertical lines. Vertical lines indicate that the work done is 0. Okay, so we're going to fill in here from A to B, the work done is 0. Now, if from A to B, the work done is 0, then we can also fill in over here using the first law of thermodynamics that the heat transferred to the gas must be 1440. Okay, next, we are given the information from B to C. From B to C, the work is done by gas 800 joules. So we're going to fill in over here negative 800 joules. Okay, and then after that, we don't have any other information, so we have to start doing some thinking. Now, one thing that we haven't mentioned so far is that for isobaric processes, that means to say horizontal lines, the work done by the gas is given by the pressure multiplied by the change in volume. Okay, so actually from C to A is an isobaric process. So you can take a look at the work done. Okay, the work done will be this triangle over here. The pressure at C is 1.2 times 10 to the power of 5 Pascal. Just check. Yeah. And then the change in the volume over here will be like 7.75. Okay. And over here, this will be 4.0. Okay. So we can calculate the work done uh, on the gas. Now, it's a compression. Since it's a compression with the volume decreasing, it's work done on the gas, which will be a positive term. All right. So let's calculate the work done on the gas from C to A. From C to A, the work done will be 1.2 times 10 to the power of 5 pressure times the change in volume, and the work done will be 450 joules on the gas. Since it's on the gas, we'll put in plus 450 joules over here. Now, so since this line C to A now has two data points, we can also work out this point over here. All right. So delta U is minus 770. Okay, is equals to Q plus 450. That means Q will be minus 1220 for this line. Okay, so now we have two data points out of this whole column. So we know that, oops, sorry, not this column. So now we have two data points out of this whole column, and we know that delta U must be equals to 0. Okay, so we can find out that the last delta U over here is minus 670. And since we have two data points on the horizontal line BC, so then we can find out this answer as well. Okay, so this is how you do the Sudoku problem. Okay, try it yourself. It's very fun. Actually, this is one of the most fun topics in our physics. Okay, and that's the end of question 13.